Hello, everyone. So, kind of towards the end of the conference, so I guess we got to force a little bit of energy. But yeah, this is a talk on interactive data visualization experience. That is a research project that we built, and the name of the tool is VizInteract. And we built it using Android Canvas and Android x86. So this is a talk primarily going to be the learnings I had from building this tool. So a little bit about myself. I started off with Java development in consultancy, then moved on to product development for a small Android email client by the name of Newton Mail. I don't know if you've used it. It's available cross-platform. Used to be called Cloud Magic. So I worked as an Android developer there. Did a little bit of UX and moved into HCI research. And I'm again back to using Android for my research project. So I guess hence my connection with Android. On the side, I also organize a Google developer group for a small city outside Vancouver. It's called Surrey. And yeah, this research project was funded by Wolfgang Sturzlinger under the Canada Research Fund for Interactive Experiences. And he's a full professor who kind of does primary researches around visual analytics and mixed reality. So to kind of give a little bit of context around the research aspect of our project, so the kind of like primary showcase for our lab is this 8 into 4K panel setup that is the largest research setup of its kind in North America. And it's also powering the visualization tool that you see here. It's called DINSpace. And this is mostly kind of like a traditional visualization tool, like Tableau or Excel, any of those tools. This is more akin to that. We have your traditional mouse-based interactions, menus, icons, pointers, all of that. But what we wanted to do was go from there to building something much more interactive and using gestures and much more facilitated by touch interactions. So the primary goal was to build an interactive data visualization tool for touch-enabled displays, which use multi-touch gestures and promote all kinds of data exploration tasks. So the first question is, of course, why Android? So the first and primary goal was to support multiple configurations. We wanted to support VA tasks, all kinds of tasks like visualization tasks, which involve construction of charts, filtering data, brushing and selection, all of that, but from lower-end devices right up to higher-end configurations. So before I actually talk about what I learned by building this, I'm going to give a small sped-up demo of all that's possible on VizInteract right now. So you have a canvas, and that's the interactive canvas. You can load up the files, any kind of data file. Once you load up, you have the dimensions on the left. You drag the dimension onto the canvas. You create a frequency histogram. You can move and interact the visualization, pinch to zoom, rotation. And the cool thing is if you bring two visualizations together, you can create a parallel coordinate plot. Or if you rotate and bring together, you create a scatter plot. You can also break up the visualizations using a flick gesture, and you have moving canvas. It's all like direct manipulation. Everything that we can facilitate using direct manipulation. If you bring visualizations from the sidebar and directly onto an existing visualization, you create a filter. You can duplicate filters. You can remove filters. So I'm just kind of like a sped-up version of whatever is possible on in the tool. You can also add categorical filters, not just numerical ones. This was the most coolest one. I think we can create a radar chart by just having the visualizations oriented as an axis and bringing it together, removing the dimension and interacting with the radar chart, of course. You can also read the data values by long pressing. So that's another touch-enabled interaction that we had. Finally, creating a scatter plot matrix by combining two scatter plots. So this is all the basic visualization charts that we support and how we built it. So what did we try and what we gave up on? So I think we probably tried all open source charting libraries. Like if you've seen these names, MP, Android Chart, Android Plot, Hello Charts, all of these are very popular open source libraries. And we also tried any chart that's, I think there's a paywall. You need to acquire an API key or something to use this. But none of these worked out for us because we required the extensibility for view transformations. We required graceful transformations from one view to another, and we had to kind of glue together to create like the custom drawing routines for all of our charts view types. So therefore, these didn't work for us, and and the primary reason was that the graceful transformation was missing from one view to another. Like we wanted the views to combine and create another compositional view. We also tried D3 in a web view. And this was interesting. There was like a significant decrease in performance, especially when it was scaling and rotation gestures with multiple graphs. And we have a data point of 700 to 800 data rows, and we loaded that up. Maybe it's inefficient web view or inefficient data loading on our end, but just that D3 was a little troublesome to get it working at the smooth experience that we wanted. So what we ended up using was simple, like it's not a complicated architecture, but just having Canvas that works on a surface view and works with our data manager using a surface holder, and then our custom gesture detector sits on top of our canvas, and we have our individual shapes and individual charts as visualization idioms that have their own individual drawing routines. So talking about the learnings from Canvas, of course, we've worked with Canvas. You're going to find a lot of these things trivial knowledge, but for me, starting to work with Canvas was really interesting. So of course, working with these kinds of complicated transformation, complicated shapes, and also free-form rotation and free-form scaling, Canvas transformation save and restore is going to be your best friend. You have to delegate a lot of that drawing logic and separate it out into using Canvas transformations and save and restore. For those who are new, I don't know how many of you are new to Canvas, but just like a quick refresher, it's just if you're trying to use Canvas, like if you want to draw a shape in a different orientation or a different configuration, the easiest way is to rotate the canvas itself, do your drawing logic in a upright fashion, and then rotate the canvas back. So canvas rotation and saving and restore really helped us. And this was really important for us because we had a lot of different view types, and all of them had separate different drawing logic. And the balancing of these save and restore calls was a little tricky. So some things that helped us in this regard was using these two helper methods. You can always get a save count, which returns the number of save calls minus the number of restore calls. And also, if you want to pop back X number of save calls from the transformation stack, you can actually use restore to count and pop back the last save calls. There was like a pilot study that we did for our tool, and we found that while doing it on the large display, a lot of people were like trying to double tap on an empty space to undo what they did. And this was interesting because we didn't think of an undo operation, and we actually had bound the gesture to brushing and linking, clearing the brushing and linking part. So we actually had to go back and implement an undo operation, and that was also a little bit of challenge that we experienced. I mean, the first way that you can do undo is you, of course, can keep all the like last X number of bitmaps from the canvas in memory as instances, and then retrieve the last bitmap and set it to the canvas. But of course, there's a limit to it. You can't. There's a big memory constraint. So the other more feasible manner for doing this is to actually have a running log of all the canvas operations. And this includes all kinds of transformations, like additions, deletions, and view transformations. The one way that you can actually do this is you can keep a parallel transformation matrix. So every time you do an operation on the canvas, you also apply it to your transformation matrix as a parallel operation. And then once the user initiates an undo operation, you actually reverse the last operation from the transformation stack. Transformation matrix, if you're not aware, it's just a standard graphics view matrix that has all the operations applied to it as transformations to the view matrix. So scale, translate, rotate, all kinds of operations. Now, like I said, you can maintain a parallel transformation matrix, but before Android 16, you were actually able to just retrieve it from the canvas by calling getMatrix, but that has been deprecated like long back, so that doesn't work anymore. And especially if you have, there's a hardware acceleration bug, so if you have hardware acceleration enabled, this value that's returned is not correct. But surprisingly, if you add the canvas to a parent view and call the getMatrix on the parent view, this actually returns the correct transformation matrix. So you can also use this instead of just applying, maintaining a parallel transformation stack. Now, all of this transformation matrix stuff is really important when it comes to doing any kind of event logic bit on the large display. And because we have like free-form rotation, free-form scaling, all of that, sometimes managing the event localization is a little tricky, like detecting event hit detections and all of that custom logic, because there's a global coordinate system and there's also a local coordinate system within each shape. So this was some kind of challenge that we faced, and I think transformation matrix also has great helper methods to help you avoid this and work with this. Is you can have a transformation matrix and then you can invert the matrix and just map the points from the world coordinate to your local coordinates. And this is important because this just abstracts away a lot of the point transformation that you'll have to do when you're trying to do custom event logic for each of the shape or each of the gestures. Now, there's an interesting thing that I'm going to point out here, and this is especially important if you're doing all these operations like scaling, rotation, translating. If you do the operations on a transformation matrix and then apply it to a bitmap to be drawn on the canvas, this is a lot slower than actually doing the operation directly on the canvas. So I would suggest if you'd want to do scaling, rotation, and translating, do direct operations on the canvas, and this is much faster. If you want to group it, like you want to do it in one shot, you can actually take the transformation matrix and concatenate it to your canvas. There's another quick canvas scale tip that I want to give out. I think if you have worked with scaling in your app, of course, you might have run into this, but this was new for me. I had problems doing the hit detection and pointer localization for when you're doing scaling and trying to do some kind of translate operation or any of the subsequent operation after scale gesture. You have to actually accommodate for the view bounds, like the clip bounds of the viewport, because your actual viewport is going to be a lot smaller than the entire canvas. So you have to first accommodate for that by introducing your scale factor and then the actual view bounds. Add the view bounds left and also top. So this is important. I think this is going to help out people who've never worked with scale and want to and have certain roadblock implementing any kind of hit detection. So yeah, this was another thing which we did, quality of life addition. We actually have a lot of overlap logic, like any kind of, there's visualization to visualization overlap detection that we need to perform. And this is especially important, let's say if you're making a radar chart and you want to add a fourth attribute, or if you're making a scatter plot, you want to add a third attribute. All of that was made much easier by using the region object. There's a corresponding region object associated with every shape. And we're doing a quick reject for doing fast overlap detection. So region quick reject was really useful. Another thing related to transformation and scaling is the way that you would scale down bitmaps. Now, there's a certain constraint that comes with Android x86. With Android x86 right now, the GPU support is really limited. Like they have some experimental support for NVIDIA cards, and AMD cards are absolutely kind of like just barely supported right now. So hardware acceleration was not something that we could do like GPU acceleration. So if you are doing Android x86 bitmap work, then if you want to scale down bitmaps, use the factory method, the create bitmap method, and don't do canvas.draw bitmap, because that is GPU enabled versus a CPU method, which is the former one. Yeah, coming to bitmap in general, of course, I think this is a no-brainer. You have to avoid creating and decoding any bitmap resources in your draw loop. And we learned it the hard way when we are trying to also do the same thing for color parsing. This was something that I didn't realize, but even color parsing from a string in your draw loop can be very computationally expensive. And while profiling, we found out that this was another roadblock. Another thing which we found out was decimal format .format, like that doesn't that is also expensive CPU wise, and I'm not that like I don't know the technical know-how for why that is, but if you guys can enlighten me on why this is an expensive operation, because we're using this for printing the axis labels, like axis point values on the graph, and this is something that we realized was not that CPU. Like this cost us a lot of CPU resources, so that was something that we avoided completely. This was, I think, the biggest benefit for us, because for multiple shapes, if you have an app that we're rendering multiple similar type of shapes, you can actually make a lot of performance improvements by just combining them to a single path and then rendering the path and in one single shot. Instead of repeatedly drawing, let's say, different rectangles, multiple rectangles or multiple ellipses, whatever. If they're common shapes, you can actually add them to one collective path. So here in this case, we have our frequency histograms. So we have multiple bars in the charts, the initial visualization. So we are using it there to actually get a lot of performance improvement. Now, talking about like how we load up data, and you can actually on a canvas work with a separate thread and do the data pre-processing or processing on a separate thread and then update your canvas. To do this, you actually have to implement a surface view and also the surface holder callback. And once you create your data manager thread, whatever data retrieval thread there is, you pass on the holder to the thread in the while you're initiating your thread, you pass on the holder, and in the thread execution loop, you actually acquire a lock on the canvas. And once you acquire the lock, you can do all of your drawing routine and then post it and then unlock the canvas. Now, this all works pretty straightforward while you're doing it in the emulator. But on a real device, I have to point out that CPU lock, like canvas locks, acquiring a canvas locks, is going to be very different. It's not a constant factor. On the emulator, it's going to be really fast, but on a real device, it can be as slow as like a second. Like this was, we were using a Galaxy Tab A as like the initial entry-level tab for our testbed, and that was really slow. But while on Android x86, you have a lot more CPU bandwidth. You have like a traditional x86 architecture running the code, so it's a lot faster there. So it was 3 milliseconds for us on Android x86. But just to point out that CPU lock, canvas lock acquisition is also dependent on the screen size. So for 80-inch, it might be different than for something you're doing on like a phone form factor or tablet form factor. Another quick surface holder, while we're talking about surface holder, there's a small performance benefit that you can actually do if you completely avoid any kind of transparency formats. Now, in our app, we completely avoided any kind of transparency bitmap formats, so 32-bit, like RGB A888, like we've just ignored it. I don't think everybody can do this. If your app needs transparency supports, you kind of have to work with it, but at the very least, you can just match the format of the bitmap with the surface holder. So the surface holder has a method set format. Just make sure if you're using, let's say, 16-bit, just set the format accordingly. Now let's come to the second part of the of the tool, which is how did we get it up on the large display. Now, in our lab, we had an access to an 80-inch Samsung 4K panel, and also a more traditionally commonly available IR touch overlay, which is developed by the guys over at PQ Labs. If you ever do any kind of capacitive IR-based overlay touch frames, you're probably just going to use the ones manufactured by PQ. The thing is, they have like great driver support for Windows. So if you just plug it into a Windows host machine and plug up the IR panel, it's going to just work fine, like everything's dandy. But the problem really occurs when you venture into like using Android x86 or any other Linux-based distro. So the common, like the question that everybody can ask is that why not just use a Windows host and use Android emulator on it and run the app? But the thing is that cannot really work, because even though the emulator supports multi-touch input, the real problem is that it's just an emulated version of it. So you have to hold down a modifier key and use the mouse to do all kinds of multi-touch events, which of course we didn't want. So this was not the experience that we were going for. So we had to look for other options. So we managed to find Android x86 as a project, it's a very actively maintained project. And it's an AOSP derivative. It's just a fork with some community submitted patches for it to be running on x86 architecture. So they have like instruction set support, and then like different kinds of motherboard, Wi-Fi chips, all that, like just to make it run on a traditional desktop. So we found Android x86, and we thought that this might be a good test bed for running our app. So the first thing that we actually tried was trying to run it on a smaller scale, like trying to get it run on a smaller setup. So we had like another 24-inch touchscreen monitor from 3M, and I just flashed an image onto a bootable USB and then ran it and tried to run it on the monitor, and it's just, everything works. And this just works out of the box because, I was completely new to driver compatibility and how Linux drivers are like supported. So it turns out 3M is a very popular touchscreen manufacturer, and their multi-touch drivers are in the upstream Linux mainline kernel. So it's just that's why it worked out, and there's no hassle that it comes with using it. So I thought, a natural extension of that would be, let's try and see. I'll take my 80-inch, the panel available, and try and run off the same bootable USB. Of course, touch input doesn't work. So it's just, it was like, I didn't realize what was the main issue. So then, of course, I thought that, 3M compatibility is much stronger than PQ Labs, even though they are really popular. Of course, the device driver support, they don't want to support, let's say, a niche user base. So that was something new for me. So I had to venture down into like the kernel module hacking. Of course, I'm not a system level, low level developer or device driver developer. So I kind of just took this as a challenge, at least to try and understand what's going on. So I did find a single point touch driver for PQ Labs developed by a community developer in the forums, PQ Labs forum, and they developed it long back for Linux 2.6.3 kernel. But I thought, because old devices are already supported in Android, not a lot can actually change, but I can use this as a good starting point. So those of you who are kind of new to device driver like me, I actually found out that to make something to get started with development, the first few things that you need is what files do you need to actually modify to, let's say, add a device driver. So usually the way it works is, this is just a high-level overview, but still, you need to add a switch in the x86 configs, so whatever configs, so 64-bit and 32-bit, you need to add the respective switch while you're configuring the kernel or making the kernel image. And then in the kconfig of that input subsystem, so if you're just adding a device driver to touchscreen, or if you're doing it for sound, correspondingly, there's going to be a kconfig file for each of those subsystems. And in that kconfig, you just add the block that represents the new device driver that you added. So in this case, our driver was supposed to be a 3-state device driver. Tri-state means like it can either be present, it cannot be present, or it can be a hot plugged module into the kernel. So it also depends on the USB, so that needs to be specified, and some helper message that you can press Y to just set up, enable the driver and all that, just for somebody who compiles or customizes this kernel in the future. There's going to be a corresponding addition in the make file, so you just add the object file that's going to be generated for your driver, and finally, the most important thing is the driver itself. Now, of course, getting into the whole device driver development might be just another topic in itself, but just to give some interesting, like the important parts, I didn't need to refer to the previous driver for understanding the product ID and vendor IDs when you're developing a device driver. These are important. And also, I had to modify the number of maximum supported points in the device driver. In this case, that was just a single point, but the touch frame that we had has 32 touch point support. So we added that. And just anybody who's curious about device drivers ever, the first good entry point to kind of see where the logic, the meat of the logic is, just go down to the probing function, the device probe function. That's usually the point where you can find some things to modify and play around with. Now, I also have to point out that I took a lot of reference and help from the 3M multi-touch device driver. And I figured out that there were some other additional parameters that I had to set, things like touch major, touch minor, and the position of the touch events. And because it's an input device driver, so there has to be a raw X and Y. Now, touch major and minor, I kind of want to give an analogy of, this was something I found on Reddit, but if you just press, let's say there's a misty window, if you press hard on it, the actual touch points that is visible is going to be the most visible part is kind of approximating the major part, and the entire finger diameter can be thought of as the minor. So this is how the touch slope or the touch point works in any kinds of touchscreen system. Position X and Y is just for any input system, you need to have that. Yeah, I also then, of course, there's a building process, and Android x86 has great documentation for building the actual kernel view, like what kind of dependencies you need, all of that. I mean, there's no point going to the depths of that, but the key thing is that if you're building on a Mac, it's a little bit of a more tricky situation because you have to install Xcode select, I think Xcode tools or something on the terminal, because Clang and Make and all of that, it installs. You can also use Homebrew for installing a lot of these dependencies, but the idea is building on Linux is a little bit more easier. So I built the image and I flashed it, and the joy I had, when those touch points showed up, the touch overlays, I was beaming with happiness, okay, now this works. But if you'll see, when I'm doing the dragging, it's delay. There's a delay, there's a significant delay in the actual touch point. So what I found out later was that this is something that you'll have to experiment for your own setup, but there's a value while you're setting the parameters for the X and Y position. It's called the fuzziness value. And this fuzziness variable, or the fuzz variable, basically indicates the amount of expected noise on the input device, and this is in terms of pixels. So what it does is this input subsystem is going to filter the input based on this value, and it does this by two things. There are two ways it does this. There's first hysteresis, and the second is smoothing. There's a lot more depth to it, but on the broader level, hysteresis is just the aspect of kind of not moving the cursor till it reaches a specific value, or there's a difference in the values. And smoothing is going to basically consider everything outside a certain threshold as a dead zone. So these are two values you'll have to, this value affects these two parameters. So you'll have to experiment. Usually the default of 0 is going to work for everyone. You don't have to change that. But in our lab, we had a lot of these lighthouse trackers for VR, and they're all IR-based. So there was a lot of noise on the frame due to these Opti trackers. So that's why the value of 10 worked with us. And just remember, every time I'm like experimenting the value, compiling the kernel, making a new image, flashing it, and then, so it's like a tedious process, but just anybody who's maybe doing this in a similar kind of setup, try with like the value of 10 or 0 and 10. Let's try that. But it worked for us. And there's a lot of software side improvements that we also had to do. This was like the device driver part, but there was also a lot of software side changes that come in when you're trying to build for a large screen, an unnaturally large screen. Velocity tracking. If you're doing any kind of velocity tracking for your app, any kind of event, touch gesture that you have implemented and uses velocity tracking, you have to keep in mind that the velocity threshold for that same action on this kind of unnaturally large surface is going to be a lot lower than what it is on a smaller form factor. And there's a reason for this. Because it's a large display, your hands kind of move very quickly versus reaching that same speed requires a lot less time compared to like on a smaller form factor. So this was really important, and this is critical if you're trying to do any kinds of velocity-based logic. You have to also accommodate for touch jitter. And this is for panels that are installed externally. If you're installing an external IR frame on the panel, it's going to be really sensitive to any kind of input movement. And these are, typically you can dial this down in the driver by some of these values, but typically I would say accommodating for touch jitter is important, because if you're relying on things like long press events, it's going to fail because the system is never going to register the long press. It's constantly going to be triggering the on move, and that's going to happen. That is what happened with us, and we had to make a small workaround for it. Like the workaround that we did was we took the view configuration threshold and just set up like a boundary for the input. So if you're within that boundary for, let's say, 300 milliseconds or so, we're going to treat it as a long press. It's just a workaround, but I'm hoping I could find, I will be able to find something much more better than this solution. Also, interesting finding, like considering the UX of actually rotating things and scaling on a large screen, you have to accommodate for any kind of scale that happens while you're rotating things. Like people don't realize this, when you're doing like rotation on a small screen, your hands, the movement in the hands is not that much. But if you're doing it on a large screen, your hands tend, like this, because it's sensitive, it also treats it as scale operation. Like there's a scale event that also gets fired. And if you want to make the experience a lot more smoother, you'll have to incorporate this perceived scaling into your code. What we did was, in the rotation gesture detector, while we have, if the angle is lesser than a certain value, in this case 10, and it was within, like the span threshold was greater than like a span pinch to zoom, we treat it as a scale operation. So yeah, this is all that we did for making on the software side. A lot of people suggest us that while you're building canvas scaling and rotation, you should actually, to optimize or make performance better, you should just pre-scale things, like have the shapes in the init function, just have it pre-scaled, all the bitmaps or whatever shapes. But that is something that we couldn't do because there was free-form scaling support, and we wanted to make the experience as natural as possible. So we had to squeeze out performances in other ways. So one way you could do it is you profile, make sure that the primitive count is less than 400, like to just achieve the 60 FPS goal. But just these are things that you can do. People suggest also to do double buffering, but we couldn't do this because it's a large display, like a 80-inch panel. So double buffering was leading to like a 20% frame rate drop. So we also avoided that. All in all, if somebody wants to recreate this setup in their own lab or in their own, like if you want to use PQ Lab setup, you wouldn't have to go through all of this. Like I submitted the driver for PQ Labs in Android x86, and it's there in upstream. So it's just going to be plug and play for most of you guys if you try ever recreating this. So I'm going to give you a small demo screen recording of, and this is an earlier version. So like how it's basically working. So the scaling and you can see that it's much easier to do scale by 2 hands instead of just doing with 1 hand. Yeah, and rotation also happens. There's just a few kinks here and there that we fixed over time, but you can clearly see that this is one of the operations that is supported, and it's working pretty well. Yeah, all of the operations, I think that's the standard. Again, you see that I'm just using 2 hands to do the scaling. So that's a little different. The UX changes when you're actually doing this kind of large display setup. Finally, I'm going to just show a real-life use case of how people can collaborate using this kind of setup to do visual analysis. And this is, again, a speed through that speed recording of that. So, yeah. So this is me and another one of a research lab assistant, and kind of just working through some visualization tasks. And you can clearly see the large display and the easy construction of visualization has led to just quickly find out insights. So that is one of the things that is this kind of gesture-driven approach can really help you. So this is just an overview of what an actual scenario might look like. So yeah. That's all that I had in terms of the things that I experimented with and what the findings were. If you ever want to talk about data visualization, Android, anything, hit me up on Twitter. And yeah, thank you for bearing with me.